So yeah, the title is on the unirationality of quadric bundles and hypersurfaces. So let me start introducing the notation. So X will be a projective variety over a field, not necessarily algebraically closed. So over a field K. And we know that the variety X is rational if there is a birational map from Pn to X. With rational, I mean rational over the base field. So Pn is Pn over the base field, and the birational map is supposed to be defined over K also. And X is unirational if there is a dominant map. From Pn to X. Let me tell you another definition, even though it's not crucial for the talk, but X is stably rational if X cross PR is rational for some R. And finally, X is rationally connected if any 2 points of X can be joined by a rational curve. So there are implications among these definitions, and X rational implies that X is stably rational, which in turn implies that X is unirational, and X unirational implies that X is rationally connected. So in general, if X is a curve or a surface over an algebraically closed field of characteristic 0, these notions are equivalent, but in dimension 3 and or higher, the first one, reverse implication, is not true. So there are examples of stably rational threefold which are not rational, and these examples are due to Beauville and Colliot-Hélène. They used these surfaces called the Chatelet surfaces. To construct a complex conic bundle. So vibration in conics. Let me call it Y. says that y is not rational, but y cross P3 is rational. This one also is not true. So unirational does not imply stably rational. And the examples here are, there are several hypersurfaces constructed by, I mean, hypersurface in Pn, constructed by Collar, Totaro, and then by Schreier. And this last implication we don't know. So this is a very important problem. I mean, to establish whether or not there are rationally connected varieties that are not unirational. Now, the MMP tells us that any variety covered by rational curves is birational equivalent to a, let's say, to a mildly singular variety Z with a contraction of relative picker number 1 and such that minus kz is pi ample. So for instance, when the dimension of Z is 3, we have 3 possibilities. With 1, W is a point, and Z is fun. And then if W is a curve, then Z is called the del pezzo fibration, so a fibration in del pezzo surfaces. And the last one, 3, is when W is a surface. And the map, D to W, is a conic bundle. So what about unirationality for these 3 classes? So you see that by the minimal model program, the unirationality of any variety curve covered by rational curve reduces to the unirationality of these 3 types of varieties. So in the first class 1, it is known that most of these are unirational. So there are very few not known cases here. One of them is the sexy double solid. is not known whether a sextic double solid so sextic double solid is a 2-to-1 cover of P3 ramified over a sextic. Sextic, I mean, whether they generate sextic double solid. And another very important case is the case of quartic triples. Sextic is unirational. And also unirationality is not known for the general quartic triplet. Okay. So what about 3, the case of conic bundles? So we know that is a theorem by Collar and Mella. A conic bundle X over P2 with discriminant of degree at most 8 is unirational. So here was the discriminant. So you have P2 and X is a fibration in conics. So the general fiber will be a smooth conic, but there are some special fibers that are rank 2 conics, like this. And the locus of P2 where the conic bundle degenerates, so where the fiber is a rank 2 conic, is a curve. And this curve is the discriminant of the conic bundle. So this theorem tells you that if the discriminant of the conic bundle is not too big, then the conic bundle is going to be unirational. So now what the connection between conic bundles, so now we want to concentrate to 2 classes of varieties. One is conic bundles or quadric bundles more generally, and the other one is hypersurfaces, more specifically quartic hypersurfaces in PN. So I told you here that it's not known whether or not the general quartic threefold is unirational, but there are examples of smooth unirational quartic threefolds. And these examples are due to Segre. So the argument goes like this. So take a quartic threefold. So hypersurface of degree 4 and P4. So this hypersurface is Fano. And so it is rationally connected. So you have plenty of rational curves in it. So take a rational curve. So, for instance, you could even take a line in X4. So now you have your X4. And you take this line in it, L. You take a point of the line. And you consider the projective tangent cone at that point. So you consider the lines passing through the chosen point that intersect X in P with multiplicity at least 3. So these lines form a cone, a quadric cone, so a cone over a conic. And you can consider the surface made like this. So you take your L and call this Y. Y is going to be the union for P varying in L of this CP, the base of the projective tangent. So this is a conic bundle over a curve, over a rational curve. So Y is a surface conic bundle. So for instance, over C, if the base field is algebraically closed, Y is rational. Now you can construct a rational map from Y to X. So take a point here. This point represents a point on your L, which is this point here. Let me call this P, LP. So it represents a point P here, and the LP is an inflection tangent. So you have this line LP intersecting X in P with multiplicity 3. But now X is as degree 4, so there must be another just one more intersection point somewhere here. Call it Y. Perhaps it's better. Call the map phi. So the fourth intersection point is going to be phi of PLP. So this way, associating to an inflection tangent the fourth intersection point, you get a rational map from Y to X, and the image of this rational map is going to be a rational surface S inside X. So S equal to phi of Y in X4 is a rational surface. So now you could redo this construction replacing the curve L with S. So here on the left, instead of the surface conic bundle, you get a conic bundle over S, over the surface S. So this is a triple conic bundle with a rational map on X4, onto X4. So this tells you that if let's call this Z. If the triple conic bundle Z is unirational, then X4 is unirational. So proving the unirationality of X4 reduces to proving the unirationality of Z. But the problem here is that this conic bundle the discriminant of Z is very big. So we don't know whether or not Z is unirational. However, you could do this construction for a quartic, an n-dimensional quartic, and what you get in this case is that you have your rational surface, but instead of the fibration in conics, you get a fibration in higher dimensional quadrics. So this is what is called a quadric bundle. And more specifically, this is a fibration in quadrics of dimension n-2. And still you have your map on X4. And now Lang's theorem tells you that the quadric fibration Z over S has a section if n is the dimension of the quadrics in the fibers is at least 5. So if the dimension of the quadrics in the fibers is at least 3. So the quadric fibration has a section, and this implies that Z is rational. So you conclude that a general quartic hypersurface of dimension at least 5 is rational. And this is true over C, because Lang's theorem works in this case works over an algebraically closed field. Okay, so you are left with the unirationality of quartics in dimension 3, quartic threefolds, and 4. So now let me tell you what I proved about the unirationality of quartics. So here. Take X4n in Pn+1 quartic, and lambda an H-plane, so a linear subspace of dimension H, and assume either then assume that either n is at least 3, h is at least 2, and the dimension of the intersection of h of lambda with the singular locus of the hypersurface is at most h-2, and X4 contains lambda. or 2, n is greater or equal than 4, h is greater or equal than 3, x for n has double points along gamma, along lambda, and the point P lying in x4 minus lambda. And the part of this, x for n is general. Then under these assumptions, x for n is unirational. So this theorem holds over an arbitrary field, I mean infinite field. And so when I say that the hypersurface contains an h-plane or has a point, I always mean the h-plane is defined over the base field and the point is defined over the base field. So it's a rational point. And so the field here is not supposed to be algebraically closed. And thanks to this theorem, now we are left with just a bunch of questions. So what's missing in this theorem? The first missing case is n equal to 3, and your quartic triple contains a line. So for instance, over C, every quartic triple contains a line. So this is the fundamental question about the unirationality of the general quartic triple over the complex numbers. And then the next one is n equal to 3, and x4 has double points along gamma, along lambda, and the dimension of lambda is either 1 or 2, so either a line or a plane. And the third case is n equal to 2, and x4 has double points along the line. And a point P not lying on the line. So this last case, so you are in P3 and you have your quartic with a double line. So projecting from the double line onto P1, you get a conic bundle structure on the quartic, just because if you take a plane containing lambda, it will intersect the quartic in 2 times lambda plus a residual curve, which is going to be a conic because the surface is degree 4. And this conic bundle vibration has exactly eight. So it would be, I mean, it would be very good to establish whether or not this is unirational, because there is another theorem by Koller and Mella saying that surface conic bundles with at most 7 singular fibers. Are unirational. So this conic bundle coming from the quartic with the double line is the first case one should consider if you want to improve Collatz and Mella result. Okay. Now, let me talk a little bit about these quadric bundles connected to the quartic surfaces. And so let me fix a bit the notation. You start with a bunch of integers. We call them A0, A, H plus 1, positive integers, with A0 greater or equal than A1 greater or equal than H plus 1. And you can consider the projectivization of A0. This is over Pn minus H plus O Pn minus H A H plus 1 with the morphism over the base. So this is a toric variety. And you have the so-called Cox coordinates on it. So the Cox ring is going to be the ring on the polynomial ring on x0 xn minus h, y0 y h plus 1, and irrelevant ideal x0 xn minus h, y0 yh plus 1, and grading (1, 0, 1, 0). So these are the degrees of the variables x0 xn minus h, minus a0 1, minus a h plus 1 1. These are the degrees of y0 yh yh plus 1. So now with these Cox coordinates, you can write down explicitly the equation of a quadric bundles inside this projective bundle. And the quadric bundle, let me call it QH, is going to be the zero locus of an equation of this form. So the sum over the ij's of sigma ij. So this sigma ij is going to be a polynomial in x0 xn minus h, and here you have yi yj. And there must be some compatibilities between the degrees of these polynomials. So if you call the ij the degree of sigma ij, then you must have the d00 minus 2a0 is equal to d01 minus a0 minus a1. And the end, this must be equal to dh plus 1 h plus 1 minus 2a h plus 1. So this means basically that this polynomial here in the definition of the quadric bundle is homogeneous with respect to the gradient we have given to our variable. So here you should imagine that you have your Pn minus h, which is the base of the fibration, and x0, xn minus h are the variables in this Pn minus h. And then you have your projective bundle with fibers of dimension h. Sorry, h plus 1. So the fiber is a ph plus 1 with variables y0, yh plus 1. So here in this equation, once you fix the x0 and minus h, you see you have a homogeneous polynomial of degree 2, which gives you a quadric in the fiber. And as before, some of these quadrics are going to be singular. And the locus of pi n minus h over which the quadrics do not have maximal rank is the discriminant of the quadric bundle. Now, clearly, in general, you cannot, I mean, in general, a quadric bundle can be, a quadric bundle over Pn minus h can be embedded in the projectivization of a vector bundle, but this vector bundle does not necessarily split, but it splits in the particular case where the base, the Pn minus h, is P1. So in that case, the ambient vector bundle will split, and this description in Cox coordinates is the general description of a quadric bundle over P1. Now, how do you attack the problem of unirationality of quadric bundles? So there is this very useful result by Enriquez that is called Enriquez criterion. Which tells you the following. If you have a fibration in quadrics, over a unirational variety, W, so saying this Enriquez criterion, you have a fibration in quadrics over unirational variety, and it tells you that QH is unirational if and only if there is a unirational variety Z in QH says that pi, let me call this map of the quadric bundle pi restricted to Z is dominant. So let me comment a bit on this Enriquez criterion. So one direction is clear. I mean, if the QH is unirational, then you have a dominant map from Pn to QH. Let's say this W is dimension n minus h, so you can take a general n minus h plane here, and its image in QH is going to be a unirational variety, better a rational variety, mapping dominantly onto the base. And conversely, if you have this transverse unirational variety, so you have to imagine that you have your fibration in quadrics. Over W. So this unirational Z, which is mapping dominantly onto W, is you should imagine it as a unirational multisection of the fibration in quadrics. So you can do a base change. The base change is going to be another quadric bundle, but in this new quadric bundle, the multisection Z will be a section Z prime. So this is a quadric bundle with a section. And so it is rational. So how do you apply this Enriquez criterion to our situation? Well, I told you that we have this result by Collar and Mella saying that if the degree of a conic bundle is of the discriminant of a conic bundle is at most 7, then the conic bundle is unirational. And so the first thing that you think of doing is cutting out the quadric bundle with hyperplane sections until you reach a conic bundle. So the idea is the following. You imagine you have your quadric bundle over, let's start with quadric bundles over P1. So here the fibers are quadrics. And you cut with hyperplane sections until you get conics inside each one of these quadrics. And call this conic bundle, let's call it Q1 n minus 3. And this is our QH. So Q1 n minus 3 is nothing but QH intersected with Y0 equal to Y1 equal to Y n minus 3 equal to 0. So if you remember, I put this order A0 greater or equal than AH plus 1. So the degrees of the polynomial, polynomials which must satisfy these relations are in decreasing order also. So here I'm cutting out with the first n minus 4 variables because I want the degree of the discriminant of the conic bundle to be as small as possible. And what you can prove is that if the degree of the discriminant, so let me call delta degree. Delta is going to be the degree of the discriminant of the quadric bundle is at most Qn 4n minus 1, then the degree of the discriminant of the conic bundle Q1 is going to be at most 7. And if this is odd, this also will be odd. And this thing that I just wrote is true with just one exception. Which is when d n minus 2 n minus 2 is equal to dn minus 1 n minus 1, which is equal to dnn, and they are all equal to 3. So there is an exception that we have to take into account, but we will deal with this later. I mean, for the time being, just concentrate on the fact that if the degree of the discriminant of the conic bundle is at most 4n minus 1, then the discriminant of the conic bundle is at most 7. So if dqh is at most 4n minus 1 and odd, then the degree of Q1 is at most 7 and odd. And so we produced inside QH a transverse unirational variety. Q1. And this is unirational by Coller's and Mella results on conic bundles. So what about the missing case? So the missing case, if you think about it, is a special quadric bundle. It is indeed a divisor of by degree (3)2 in P1 plus Pn. And here there is a construction due to Otten, which goes as follows. So you have your quadric bundle. We call it Qn plus 1, Qn minus 1 over P1. This is our 3-2 divisor in Pn times Pn. And Otten constructed a small birational map to another variety. We call it Qn minus 1 plus. And this variety comes with a morphism onto P2. And the fibers of P2 are complete intersections of two quadrics. So it seems that the situation on the right is somehow more complicated than the situation on the left, because here you had fibration, a fibration in quadrics, and now you transformed it into a fibration in complete intersections of two quadrics. But what you can do on this side, and here you have your complete intersection of two quadrics. So you take a point here on the left, which is not in the base locus of the map. You look at the image. Psi of P. So now this fiber here, call it V. So V is a complete intersection of two quadrics with a point, and it is known to be unirational. The simplest example is the complete intersection of two quadrics in P4. This is a del pezzo surface of degree 4 with a point which is unirational. Clearly here I'm taking complete intersection of two quadrics in Pn with n at least 4, because in P3 it is not true. I mean, it is an elliptic curve. So at the end, if you put all of this together, you prove the following theorem. So you have Qn minus 1 onto P1 a quadric bundle says that the top self-intersection of the anti-canonical bundle is positive. This condition on the positivity of the top self-intersection of the conic bundle is exactly equivalent to the discriminant of the conic bundle of the quadric bundle as a degree at most for n-1. These two are equivalent, and dqn-1 is odd. So if either n is at most 5, the quadric bundle is a point, or 2, the base field K is a number field, so if the base field is a number field, you don't need this additional hypothesis of the dimension being at most 5. Then Qn-1 is unirational. So this is for quadric bundles over P1, but over an arbitrary field. And now, how do you go from quadric bundles over P1 to quadric bundles over Pn? Well, if you have your a quadric bundle over Pn minus h, let's say over the field of complex numbers. So this QH over C. You take a point in Pn minus h, and you project from the point. Like let us do the example of P2. You project from the point onto P1, and the generic fiber of this projection, let's call it QH eta, is a quadric bundle over P1, but P1 is over the function field of P1, over C of t. So we have a quadric bundle over P1 now, but we pay the price that the field is not C anymore, is the function field C of t. But now you can use the theorem you had before for quadric bundles over P1. And if we know that if QH of eta is unirational over C of t, then QH is unirational over C. And for instance, as an application of this, you have the following corollary for quadric bundles, surface quadric bundle over P2 over C. So this is a fibration in two-dimensional quadrics. If the discriminant curve of the quadric bundle has degree at most 12, then Q2 is unirational. And this is true not just for the general quadric bundle with discriminant curve of degree 12, but it's true for any smooth quadric bundle Q2. Okay, so this is a sort of generalization in higher dimension of the theorem by Koller and Mell. Okay, so I think I will stop here if you have questions.